of Computer Sciences, and he loves history. So today he's going to talk about history of mathematics. Now I don't understand computer science, history, and mathematics why they are combined. So to clear this confusion, we have Ashutosh here.
So let's give Ashutosh a huge round of applause.
Hi everyone, I'm Ashutosh, and today I'll be giving a very quick, very whirlwind tour of historical Indian mathematics. And I'm in the computer science department, but the reason I chose this topic is that I've observed that when I'm talking to my family or like other people I meet, I find that most people aren't aware of what historical Indian mathematicians actually did. People have heard the names, Aryabhata, this, that. People know maybe zero, somebody invented zero. So that is why I titled it Beyond Zero, because I want to share more of what I've learned about this. So nowadays we know that mathematics is in everything. It's in technology, it is in engineering, it is in all of the things that we are familiar with now. But even historical mathematicians realize that it is present in everything. So this is a poem by the mathematician Mahavira, not the Jain saint Mahavira, different Mahavira. Mathematics finds use in matters that are worldly as well as spiritual, in trade, in pleasure, in music and theater, in the culinary arts, in medicine, in architecture, in grammar, in poetry. In all of these disciplines, mathematics is omnipresent and supreme. So this is in praise of mathematics, and this is why we should study and learn mathematics. So let us jump right in with an example, and then I will talk a bit about what is actually going on here. So here is a line. Tribhujasya phala shariram samadala koti bhujarda samvargaha. Now, if I told you this out of context, and if you didn't know that this was a talk about mathematics, you might think that this is in praise of a god, or you might think that this is some moral verse. It is telling you, teaching you some morals. But actually, this is not what it is. It is actually the formula for area of a triangle. So this is this line is written by Aryabhata, but of course, area of a triangle was known before, but this nice short expression was written by him. So what this says is Tribhujasya phala shariram, means the body or the area of a triangle, is Samadala Koti is the Sanskrit mathematical term for a perpendicular. Bhujartha is half a side. And Samvargaha is it's telling you what to do. It's telling you to multiply the two. So if you want the area of a triangle, measure the perpendicular, measure half a side, and multiply and get the area. Nowadays, the formula that you would have learned maybe in middle school is A equals half times H times B. This is an equation. We've learned it as an equation, but he has written it as a Sanskrit sentence. Why? Because in those times, the normal thing to do was, if you have a theorem or a formula, the normal thing to do was write it as a sentence, write it as how you will understand it, rather than as an algebraic expression. The algebraic way of writing was much later, maybe 15th century or so. In those days, this was the normal way to write down and communicate what you have observed. Even when numbers were written, and later we'll see some examples of this, the numbers would be written as words, and later the numerals that now we call Hindu numerals or Indo-Arabic numerals, they were developed in India. That came a bit later as well. And when they wrote their books, they would also the books were intended for students. So if they were intended for students to learn how to solve a particular type of problem. So there would be a problem, and as you solve the problem, you will also learn the method to solve other problems of the same type. And we will see a lot of examples of this. And there was less of an emphasis on proofs. So for instance, Aryabhata's statements, they are just written as they are. They were his empirical observations. The way that we write mathematics has changed over the years. So now, of course, if you ever publish a theorem, you better include a proof. But in those days, the normal thing to do was write what you have observed. If it's correct, it will stand the test of time. If it is wrong, somebody will correct. One more thing, why did people study this? So there were 6 branches of learning at the time. They are called Vedangas. So the Vedas themselves did not necessarily contain mathematics per se. So when we say Vedic mathematics, for instance, it doesn't mean mathematics in the Vedas. There is not mathematics in the Vedas. But to carry out what the Vedas tell you to do, build a temple a certain way, celebrate a festival at a certain time, do this when the planets are in this alignment. To do that, you need to do studies. So in order to do this understanding, to carry out the Vedas correctly, that was the stated aim. So to do that is why they started all of these branches of study. So it included grammar, astronomy, astrology, as well as, of course, mathematics. But of course, they were driven by their own curiosity and they went far beyond just the limits of what the Vedas told you to do. There were also books from the Vedic era. I will mention one or two later. But we are talking, mostly I'll be talking about people who are a fair bit later than the Vedas. So now for a very quick tour of various areas of mathematics and what Indian mathematicians actually contributed to them. So in geometry, I already mentioned the area of a triangle. The other very fundamental theorem relating to triangles is the Pythagorean theorem. So actually this was known even before Bodhayana Sutra, and this actually goes back to the Vedic period. So you will notice that some textbooks might call the Pythagorean theorem as Bodhayana's theorem. This is why. But this nice short expression was written by Aryabhata. Aryabhata also wrote down an expression for the volume of a tetrahedron. What this says is the volume is half times this ardha, as you might recognize from before, means half times base area times height. This is the expression for volume of a tetrahedron that was written by Aryabhata. This is actually wrong. That half is supposed to be 1/3. So this was corrected a few decades later by Brahmagupta, who was writing his commentaries and so on the works of Aryabhata, and he found this error and he corrected. So the long back equivalent of what we now call as peer review or finding somebody else's correcting somebody else's work started back then in this way. Some more stuff from geometry. So here is an expression by Aryabhata for the area of a circle, and it's very nicely written. So it just says half of the perimeter or circumference. You might recall that the circumference is 2 pi r. So the half of that is just pi r times half of the diameter, which is radius, which is just r. So pi r into r, which is pi r squared, which is the area formula that you have learned. And this is it's very nicely written. It doesn't mention pi anywhere. Because pi is irrational, transcendental, and there aren't clean ways to say it. But this is a nice expression just in terms of other parameters of the circle itself. So you might ask, did Aryabhata not know about pi? Did he, did he not try to approximate it or anything? He did. He wrote an approximation for pi like this. So what he says is, if the diameter is 20,000 units, 20,000 of something, or if the radius is 10,000 of something, then the circumference would be this. It would be 62,382. This is his observation about how circles occur. So if the radius is this, then the circumference would be this, which is in other words an approximation for pi. He recognized that it was an approximation. So this word asanna means that it is not exact. It is an approximation, and it's actually a very good approximation. It goes to 4 decimal places, which is very good for that time. Here are some problems from permutations and combination. I'm going to ask some of you to give me answers. So here is a question from Brahmagupta's book. He says, so suppose Lord Shiva, in some forms, he has 10 hands. So suppose he has 10 weapons. How many possible arrangements of these are there can he have? If he is arranging these 10 weapons in his 10 hands, how many possible arrangements are there? Now, if 10 is a very big number and it's a bit hard to work with, here's a simpler case. Vishnu has 4 arms and he has 4 objects that he holds. So how many arrangements of those are there? If you look at statues and all, you'll only find 1 or 2. But how many possibilities are there? So, yeah. Very good. And 10? Yeah. I also didn't simplify 10 factorial. It's a very big number. But yeah, that's it. So 10 factorial and 4 factorial. So if you are a student and you are studying Brahmagupta's book, when you're doing this, you will, it makes you write down the factorials of these numbers and how to compute factorials in general. Here's another question. This is, so Sushruta is, okay, it's a bit complicated. He was not one person. There are many people considered to be Sushruta. But one particular Sushruta wrote about, the culinary arts, different kinds of cooking. And this is a mathematics question from there. So suppose there are 6 tastes. Now, I don't know, maybe in Hindi or Marathi, you might have a word for it. In Tamil, we definitely have a word for 6 different tastes. We call it arusuvai. So now there are 6 savors. And usually a food will have a combination of them, right? You might have a biryani that is salty and spicy. You might have a chutney that is sweet and sour. So how many possible ways are there of combining these 6? And I want you to tell me systematically. So how many ways are there? Well, with one taste, you can just have one with each. With 2, there are 6 choices for the first one, and there are 5 choices for the second one. But we are double counting here, right? We might choose sweet and sour, or we might choose sour and sweet. So to avoid the double counting, we have to divide by 2 to give 15. So that is, if some of you have seen combinatorics notation, you would have seen it as 6 choose 2. If you don't know it, don't worry. And with 3 tastes, similarly 6, 5, 4 choices for the 3. But you have to, you're over counting again, so you have to divide by 3 times 2 to get 6 choose 3. And this, if you do this, you get a total of 63, which is also 2 to the power 6 minus 1. Why minus 1? Because you can't have something with no taste. You can have water with no taste, but I'm not counting that. Again, so a student who is studying this is forced to write down 6 choose 1, 6 choose 2, and so on, and it teaches the student. So another way of counting how many ways are there of making something with 6 tastes is 2 to the 6. Because sweet, yes or no. Sour, yes or no. Salty, yes or no. So 2 times 2 times 2 times 2, 6 times. So that is 2 to the 6. But that also includes the case when you are saying no for all 6 tastes. When you are not including any of them. So then that is a completely tasteless food. We are not including that in this. So that is another way of arriving at 63. The other way is, of course, 6 plus 15 plus 20 plus, you'll get another 15 and another 6 and another 1. Yeah? If you have seen these permutations and these 6 choose 2 kind of things, it will immediately remind you of something called binomial theorem. Binomial theorem is, if you have 2 things, a plus b, and you want to write down what is a plus b squared, a plus b cubed, a plus b to the 4. This is the binomial theorem tells you how to do this. So a plus b to the 0, anything power 0 is 1. So that is just 1. A plus b to the 1 is just a plus b. A plus b squared, this is where it gets interesting. A squared plus 2ab plus b squared. A plus b to the cubed, a cubed plus 3a squared b plus 3ab squared plus b cubed. Now, if you forget about a and b, if you just look at the numbers, there's a 1 here, 1, 1, 1, 2, 1, 1, 3, 3, 1, right? Just look at the numbers. Now, there is something nice happening here. This was studied by Pingala, who's in the picture. So, he wrote down just the numbers occurring here in a triangle. He called it Meru Prastara. This was, many centuries before Pascal's triangle, but this is how we normally call it now, Pascal's triangle. So, the 1, 1, 2, 1, 1, 3, 3, 1 that we saw earlier, and then for 4, for 5, and so on. A nice thing that you might notice here is, if you have one row, how to get the next row? Does anybody observe any pattern in how to get the next row from the previous row? Yes, very nice. So the first and last will be 1. The middle ones, this 5 is equal to 1 plus 4. This 10 is equal to 4 plus 6. This 10 is equal to 6 plus 4. This 5 is equal to 4 plus 1. This is just a 1. Now the next row, if you want to get, you do 1 plus 5, 5 plus 10, 10 plus 10. So this is a Meru Prastara with this very nice property that he wrote down. Actually, his motivation for studying this was poetry. So I will come back to this. So remember that, because I'll come back to it later. Here are a couple of problems from the field of series and progressions. Now, this is a expression by Sridharacharya. So he is telling you how to get 1 plus 2 plus 3 plus 4 plus 5 up to some n. If you want to go up till n, what is the total sum up till then? So what he tells you the sum is, well, what are we trying to compute? The first term is unity, 1. The common difference is also unity, which means you're going consecutive numbers, 1, 2, 3, 4, 5. Then what is the sum? The sum is equal to half times the number of terms n and the number of terms plus 1, n plus 1. So this is Sridharacharya's formula for adding up numbers, 1 plus 2 plus 3 plus 4 up to n. How do you get this? Again, he didn't include a proof, like I said. But if you want to convince yourself of this, This is 1, 2, 3, 4. You want to add up these. You can just, if you're adding up till n, you can copy this whole triangle again to get a rectangle. And a rectangle is very easy to count how many things are there. It's just this side times that side. So if you stack these two triangles like this, you get one side has 4. 4 is what you're trying to compute. 1 plus 2 plus 3 plus 4. And the other side is 5 because you have stacked them. So 4 times 5 divided by 2. Now, a more general form, we saw 1 plus 2 plus 3 plus 4. A more general form is any arithmetic progression. Arithmetic progression means between any two next terms, the difference is the same. So you start with A plus D, A plus 2D, A plus 3D, and so on up till some n times you do this. Now, what is the sum of this? So this formula was known by many people. It was written down by many people. And many of them, Brahmagupta, Bhaskara, in their books, they have problems of this type. So now there are 4 things, right? Sn is the sum. This is the expression for the sum. This you can get by, if you want to convince yourself of this, you can pair up this, the first and the last. So you get 2a plus n minus 1d. You pair up the second and the second last also, you get this. You keep doing this and n by 2 number of times. So that's how you get this formula. And many of them have problems of this type. So out of these 4 things, Sn, N, A, D, they'll give you any 3 and you have to find the 4th. Many of them have this pattern. But one of these patterns is more interesting than the other. So here is an example. This is from Bhaskara, the first book. So he gives you the common difference, 9. He gives you the first term, 8. And he tells you the sum. What is the number of terms? Now, what is happening here? This is a bit interesting because this is the same formula from the last slide. So now we have Sn, we have A, he has given you A, we have D, he has given you. But there is an N here and there is an N inside. So N is multiplied by N, which means that you have a quadratic equation. So now what he's actually asking you to do is to solve a quadratic equation. So now if you want to solve this, you better know how to solve quadratic equations. And yes, it is true that many of them tackled this problem of how to solve a quadratic equation. So now let us look at some of the problems from algebra equations. But before we come to quadratic equations, let us look at some simpler cases. So this theory was formalized by Brahmagupta. So he had a theory of positive numbers, negative numbers, 0, and various operations. So what happens? So positive plus positive is positive, positive times positive is also positive, negative times negative is positive, but negative plus negative is negative. All of these things he wrote down. And also what happens when you add 0, nothing happens. When you multiply by 0, it becomes 0. He also wrote about dividing by 0, which is not how we do it today. He wrote that 0 divided by 0 is 0. So this is something that we have learned since then, that we shouldn't do such things. And he also developed a notation for polynomials. So if you have something, x cube plus 3xy, he had a Sanskrit notation for writing this. But the procedures for solving different kinds of equations go back to even before Brahmagupta. So what were some of them? Well, here is a simple linear equation, and this one I'm going to ask you the answer. So start working it out. So there is a number. It is multiplied by 2, then increased by 1, divided by 5, multiplied by 3, diminished by 2, that is reduced by 2, then divided by 7 to get the result 1. So what is the number? So what this is teaching you to do is, now that you have the end result, work backwards to get the answer. Yeah, 7 is right. So how do you work backwards to get the answer? You have 1 as the result. Something was divided by 7 to get 1. So what should it be? 7. Then something was diminished by 2. It was reduced by 2 to get 7. So what was it? 9. Multiplied by 3 to get 9. So it must be, yeah. Something was divided by 5 to get 3. So it must be 15. Something was increased by 1 to get 15. 14. Something was multiplied by 2 to get 14. 7. So the original number must have been 7. So this is how it's instructing you to solve it. The answer is 7. Here is a question in modular arithmetic. Now, some of you would, in the older ones among you would know, may know like what theorem this is referring to or something. But this is a question in remainders. So a number leaves 1 as the remainder when it's divided by 5 and 2 as the remainder when it is divided by 7. What is the number? 16. Yeah, some of you who have studied more maths might have heard the term Chinese remainder theorem or something. But these are the questions in those. Now, till then we saw questions, problems with one variable. Here's a problem with two variables. When two numbers are added, it gives 101. And when they are subtracted, the difference is 25. What are the two numbers? Yeah. 63 and 38. Very good. So, how the answer, the two numbers are 63 and 38. And the procedure that he gave and also some others wrote down formally is, if you know the sum of two numbers, x plus y is sum a, and you know the difference, x minus y is b, then x better be a plus b by 2 and y is a minus b by 2. Yeah. Now, finally, what I've been teasing from the beginning, which is quadratic equation in one variable. There were approximations and procedures known by other people, but this is a nice expression given by Brahmagupta himself. So what he does, what he tells you is, if you have this equation, ax squared plus bx equals c, not how we write it today, but this is how they wrote it then. First multiply 4 times the coefficient of the square. So first multiply by 4a, then add on both sides the square of the middle coefficient. So add a b squared on both sides. Does anybody recognize the right hand side? Yeah, it's what comes in the quadratic formula. And the left hand side is actually a square. So now you can take the square root on both sides, and then you'll have something linear in x. So then you can solve for x. And I suppose at that time they were mostly concerned with the positive square root or the higher square root. So it doesn't talk about two solutions, two square roots and so on. But this is exactly what we call the quadratic formula. Now let us move away from equations to some applications in language and literature. So I won't say very much about this, but Panini lived a very long time ago, and the grammar that he gave for Sanskrit was what we call a generative grammar. So we still talk this way in computer science and in linguistics. That given, so it tells you the building blocks and it tells you how to put them together. So in Sanskrit, you can start with the building blocks and put them together to make bigger sentences, bigger statements. Now let us look at a question from poetry, which I had put up in earlier. Now in Sanskrit, there are two types of syllables. There are laghu and guru. There are light ones and heavy ones. For instance, ka is light and ka is heavy. So even if you don't know which is which, we will denote them by G and L. And now we'll do some questions with counting how many possibilities are there. So here's a question from Pingala. Suppose I'm allowing you to use 10 syllables of any kind. How many possibilities are there of each arrangement of Laghu and Guru? This is the question put forth by Pingala. And if you remember where he came up earlier, that will also give you a hint to the answer. The answer is, if they're all Guru, there is only one way. It's just all of them Guru. If there is one Laghu, then there are 10 possibilities for which one that Laghu could be. It could be the first, second, third, fourth. So there are 10 possibilities. If there are two, then there are 10 times 9 divided by 2 because of that double counting thing from earlier. Yeah. And if this looks familiar, this is the 10th row of the Meru Prastara from earlier. So this is actually his motivation for studying. Now here's a slightly different, more involved question maybe. Suppose you would have noticed that this ka is sort of longer than ka, right? It's in fact twice as long. So we will say that, suppose we imagine that ka takes 2 seconds to say and ka takes only 1 second to say, or just some kind of unit. Now I'm telling you that you have 10 of these units available. How many ways are there to fill them? This is an interesting question, right? Because there are so many ways that we could do it. For instance, we could just have 5 heavy ones because each one is 2 seconds. So we could have 5 heavy things, or we could have 10 light things, or we could have some alternating combination of the two. So there are so many, right? So the question is, how many ways are there of doing this? So this question was studied by Hemachandra over there. Any ideas on how to do it? Okay, let us see how Hemachandra went about it. So let us call this number H10. You don't have to worry about, we could call it anything. Let us call it H10 because it is the number of ways of filling 10. Now there are two cases, right? For what the first one you choose, it could be either heavy or light. So suppose it is light. Now there are 9 seconds left. So now the number of ways of filling 9 seconds is what we want. Is this clear? If the first one is light, then there are 9 seconds left, 9 units left. If the first one is heavy, then there are 8 units left. So there are two cases. The first one is light, 9 seconds left. First one is heavy, 8 seconds left. And then the total number of ways will depend on these two. How does it depend on the two? Does anyone seeing the relationship? H10 is equal to H9 plus H8, right? Because there are two possibilities. Either there are 9 left or there are 8 left. And H10 is going to be the total of both of them. Does anybody recognize the expression that looks like this? Not quite the triangle thing. So where the nth term is the sum of the previous two terms. Anybody know what this is called? Yeah. So nowadays we call them Fibonacci numbers. And in Sanskrit they are known as Himachandra numbers because he studied this problem and he named them this. So Fibonacci's motivation was something different. It was some rabbits are breeding and like how many rabbits are going to be there. This is also a very nice motivation for how these Fibonacci numbers come about, also known as Hemachandra numbers. So we looked at so many things. We looked at geometry, we looked at series, progressions, equations, permutations, combinations, and there are so many other fields that they studied, and honestly, each of them is worthy of a talk on its own. So methods of solving indeterminate equations. What I mean by that is, maybe you have only one equation, but there are two variables. For example, x squared plus x equals y squared. Now you have two variables and only one equation. Of course, there are infinitely many solutions, but how to generate integer solutions for these? You want integers that satisfy this relation. How to do it? So there's a very nice theory developed by Brahmagupta and others on how to go about solving this. Then calculus worked on by Madhava and some others. Then loans, simple interest, compound interest, bodies in motion. So very pure kinematics problems of two bodies are moving towards each other, away from each other. What are the speeds? How do they interact? And many of these were in service of astronomy. So they had a very advanced understanding of astronomy. So bodies in space, their orbits, how celestial events occur, eclipses, other such things. They had a very good understanding of these things. The motivation was, of course, to understand a calendar, to understand these things. But out of curiosity, they had a good understanding of the universe. And definitely, I bolded it because it is a very vast field in itself. So here are some takeaways for you. So the way they worked was they were motivated by some practical applications, but they were just curious by themselves. And the way they did their work was many of them wrote commentaries on the work of others. And in the process, they would correct mistakes that they had made, or they would make more explanations, create problems so that students learning can understand better. So the work was building on the work of others. And in case you have ever seen anybody overstate or understate the extent of the work that these people did, well, there is no need to do that. What they did is quite remarkable and quite interesting. And if you found this to be an interesting quick tour, then I really encourage you to find out more. So these are the sources that I used for this. Talks and articles by Gopu from this blog, which you can check out if you are interested in more, and this book. These are the original books and some others that I didn't mention. These ones, yes, there are translations available in English as well as other Indian language. And many of these also contain problems that you can try your hand at. Okay, I'll leave with a problem. I won't tell you the answer. This is for you to go home and work out. So a hawk is sitting on top of a wall of height 12 cubits. A cubit is this much, but you don't have to worry about how much it is. I just want to answer in terms of also cubits. It sees a rat at a horizontal distance of 24 cubits away from the base of the wall. The rat is frightened seeing this hawk and it starts running, but it runs towards the wall because its home is at the base of the wall. but the hawk flies towards it and catches it. Assume that they have the same speed. How far did the rat run? This is for you to work on. And this is, you can solve it using things that I mentioned before. So that is the end of my talk. Thank you.
Thank you, Ashutosh, for journeying through the numbers. So now the podium is open for questions. And I must say, like, very intelligent audience.
Yeah, thank you for answering my question. I was afraid that I would just ask and nobody would answer. So thank you.
Yes, we have a question there.
Thank you.
Hello. Yeah. So in one of the slides on Sanskrit grammar, Panini, you have used the word generative grammar or generative language. So why is that generative is used there? Isn't this a definite
So
grammar?
it is generative as in it tells you how to combine smaller things to get bigger things. So you can generate longer words and longer sentences from the particles. So that is what I mean by generative. So it tells you how to generate. It's not, it is definitive as in he defines, for instance, there is this Ayun, Rilith, you might have heard this thing. So those are the individual alphabets that are allowed. Then it tells you how you are allowed to combine. So the generative means that, to generate from this. Yes, there was, you had a question?
More questions?
लास्ट वाले क्वेश्चन का आंसर मिल गया?
A hint. Okay, suppose the hawk flew a distance of x diagonally. Then the rat also would have, because it's the same amount of time, the rat also would have run some x. So now you have a right angle triangle.
So now I have a question for the audience. Like, what is the value of H10? You know, H10 is equal to H9 plus H8, but tell me in numbers.
So the easier thing to do is start with h1 and h2. Then every next term is equal to the sum of the two previous. So if you have a pen and paper, it's very easy. If you're doing it in your mind, good luck. Sorry? 55. Is that right?
I don't know. I have to check. The audience is really intelligent.
Yeah, 55 is in the sequence. I don't remember the index. Yeah. Yeah, so all of these are in the Fibonacci series. I don't remember which is the 10th. So one of you must be right.
55.
One system.
So you should remember your base case. Your base case is you have only one syllable.
10th बोला था.
There are two ways to do it. Actually. You have only 1 second. There's only one way to do it, which is one light.
I think 55 is the correct answer. I'm not sure. What is the value of H1?
H1, how many ways are there of filling only 1 second? One. Only one light you are allowed.
And H2?
How many ways are there of filling 2 seconds? 2 ways, no? Because you can either have one heavy syllable or two light syllables. So you have H1 is 1, H2 is 2. Now you have to just add every...
So Fibonacci series usually starts from 1, 1 and then it comes to 2. So H10 will be equal to 11th number of the Fibonacci series, which is 89. So the 55 was pretty close because it was 10th number, but we have to go to the 11th one.
Good work. You're the only one who got it. Yeah. Okay, this is it's a question to take home, so you can don't spoil it. You can tell me afterwards. I want everyone to solve it when they go home.
Okay, I think with this we can close the question answer rounds and go for the next speaker. Thank you, Ashutosh, once again. Can you have a